Okay, hi everyone. I'm Sadie Newholm. This is Erin Rogo and Tim Angelou, and we'll be presenting the final oral report, the robotic kicker. To the right of the screen is Stephen Byers, Scott Brown, and John White, and they will be here to answer any questions at the end of the presentation. So just a brief overview of what we're going to go over today. We're going to go through our objective, our building process, and any variations from our initial design. Then I'm going to hand it off to Aaron, and he's going to talk about testing results, and then go into some more detail about the electrical systems. Finally, Tim's going to talk about the mechanical systems, our budget, any future work we have for Velva Robotics to pick up, and what we've learned throughout this process. So as a reminder of our objective, we wanted to build a robotic kicker that was accurate, repeatable, and could kick a variable distance. And beyond that, we wanted to be better than the previous iterations. As some of you may know, this is the third iteration of the Robotic Kicker Senior Design Project, so hopefully it will be the last, assuming that we've done well enough to provide what our customers wanted. So a bit about our design process this semester. The majority of our design was finished in December. We actually started ordering parts as early as Thanksgiving break. So the main goals for this semester was our T and foot design. As we mentioned, we had iterative processes to determine the best designs for those. And we also did some iterative motor testing to find the best motor and gearbox combination for our kicker. So a bit about our building process throughout the semester. We started by building our base drivetrain. That's the picture in the upper right-hand corner. That's just the HDPE base along with our motors and wheels for that. Our second step was at what we affectionately call Peg Leg Man. He's the second picture down there. It's actually the free swinging portion of our 4-bar mechanism. We then built our electrical systems. That's the third system down there. That was actually our first milestone. That included all the electrical, including the motor for the kick, as well as the IR sensor safety. Finally, we welded supports and mounted the mechanism. That'll be the fourth picture down. And then, again, as I mentioned earlier, we finalized our foot and T design and finally mounted our kicking motor. So we did have a couple of variations from our initial design, the main one being the addition of surgical tubing to our mechanism. So you can see there in the picture, we have added surgical tubings at point A, B, and C. Points A and B are running in parallel, so B is that line in the front there, and then A is directly behind it, pretty much mirrored from it. And then C is between the foot and the mechanism, so it pulls the foot kind of towards the ball in its final kick. So we can vary our kicks through changing the number of rungs of surgical tubing at those 3 points. Our furthest kick, which can range from 80 to 90 feet, has 2 rungs of surgical tubing at each of those 3 locations, and then we can put it all the way down to no surgical tubing at all to get a kick that's 10 to 20 feet. So we have a wide range of kicking distances through those variations. We also had to change our initial motor mount location. This is because of the surgical tubing. We needed to push the 4-bar mechanism farther back into a dead zone so it wouldn't actuate itself. And then we also added a mechanical stop to the top of that, because when we have 2 bands of surgical tubing at each of those locations mentioned, it does try to self-activate without pressing the button, as well as an additional safety for the other setups as well. We also added a decorative side panel, which you can kind of see in the picture on the right there. It's like Charlie Brown, which is the name of our kicker, and it has the number on it for our actual games. We also added a laser sight so we could align the robot to where we want it to kick. And we decided to keep our 3D printed foot over our metal foot, as we found that a momentum change through speed was more beneficial for us over a momentum change through mass. So now I'm going to hand this over to Aaron, and he's going to talk to you about testing.
Thank you. For our testing requirements, 2 of our requirements were for field goals and for punts, and so we went to the ARC to test these. For our field goals, we were required to have 95% accuracy at 50 feet, and testing this with 20 kicks to get that resolution, we found that we had 100% accuracy. So that was very favorable results. For punt distances, we wanted to be able to have the ball stop consistently between 30 and 60 feet. This was so that in a kickoff, we could punt the ball without causing a touchback by the ball rolling into the end zone. So here we have a box and whisker plot diagram of our impact distance where the ball first strikes the ground, and then the resting distance where it comes to a rolling stop. And then the orange is our targeted range. As you can see, we had very consistent impact distances, but then it's a football. So you can never predict where a football is going to go. So it's a little bit more scattered on the resting distance, but we can see that we are still within the targeted range with 1 standard deviation. Aside from our actual performance requirements, we also had to test our maintenance requirements. So we required that a pit crew would be able to remove the kicking motor and put on a replacement and make other various maintenance tasks completed within a certain amount of time. So we had Valpo Robotics pit crew run those tests for us with our help, and we found that we were able to meet all the timing requirements for that. Our results were very favorable as well. Here, as we've seen in other OPRs, is a punt from our actual playoffs games. This is one of those outliers from the previous test results. As you can see, it does roll into the end zone. This is something that the whole league actually struggles with right now, of everyone's kickers are a little excited. But our field goals were also very favorable. This one was also overpowered because we were ready for a 50-foot field goal before having a surprise touchdown. And so the ball actually goes straight up and out of frame, but it's still spot on accurate and got us the points. We also, I think our farthest field goals that was successful during playoffs was over 70 feet and almost hit Professor Vinstrom's kid in the face. But aside from that, very favorable results during the game as well. So now let's take a step back and look at how the system actually works. So this is our original electrical system that we started at in our design phase. We have a PS3 controller that the user can provide input through that communicates over a standard Bluetooth protocol with an Arduino microprocessor that has a Bluetooth interface. This whole system runs on a 12-volt battery supply that is standard across all of Valpo Robotics team members so that it's consistent with the rest of the team. This microprocessor provides control input to 3 Victor 888 speed controllers. 2 of those control RS550 motors that consist of the drivetrain, and then another one is also interfaced with an IR sensor to detect whether a football is in the kicking tee, and then that controls whether or not it then actuates the kicking motor. This kicking motor operates more as in a starting force for the kicking mechanism now because of our additional surgical tubing that then takes over mid-swing. Now we have also added a key switch to this kicking motor as well. This key switch is run in line with the power to the speed controller. And so when this key switch is turned off, we know that no power is getting to the kicking motor, and so we know that there's no risk of it accidentally activating. We've also added a servo to control the mechanical lock that Sadie covered earlier, and this is also controlled by a PWM lock. As far as our locking mechanism goes, earlier we showed you this flowchart of the locking logic. The time was fairly simple, but now that we've added more peripherals, it's gotten a little bit more complicated. So this is what it looks like now. At the start of our logic, we have a block that allows the user to lock the mechanism. Once the mechanism has been locked, there's no way for it to become unlocked unless a football is in the tee. Right here is a question of whether or not the IR system has been triggered for more than 2 seconds by a football in the tee. It's more than 2 seconds so that we don't run the risk of someone passing their hand through and all of a sudden it actuating. So once there is a football in the key, in the tee, then the user can unlock the mechanical lock, and then this allows it to actuate. There's also a software lock so that the motor cannot actuate until the mechanical lock is disengaged. So once all of these criteria have been met, then the person controlling the robot can actually kick the ball. But still won't actually kick the ball unless you've turned on that key controlling the motor. So several different layers of safety to make sure that we don't have any accidental kicks. For our control system, we have a basic drive system. On the left joystick, we have forward and backward motion. On the right joystick, we have left and right turning. This was a design choice to make it more like what you'd see in a racing video game, something like that, so that's a little easier for just anyone to pick up. This is in contrast to what's called tank drive, which is another common drive scheme in robotics, where each drive wheel is given independent control from the joystick. So both joysticks would provide forward and backward motion, but only for one wheel at a time. We have connect and disconnect ability through the, I think it's called the PS button, the middle button there, and then the upper right hand button there toggles the mechanical lock, but of course it's subject to the logic I've covered previously. And then with triangle we can request a kick. Previously we also had varying levels of kick controlled by a software from circle, cross, and square. But with the addition of surgical tubing, this became less relevant of what the motor was actually doing, and it was more relevant what the surgical tubing was doing. So now it's just simplified to just use triangle. Now Tim will give us an overview of the mechanical systems.
Thank you, Aaron. All right, so for our mechanical systems, we had two primary subsystems as our mechanical components. We had our drivetrain and we had our four-bar kicking mechanism. For the drivetrain, it remained pretty unchanged throughout the course of our design and build process. Most of the drivetrain consisted of parts that were donated via Valpo Robotics, so that included our Victor 888 speed controllers, our BaneBots RS550 motors, the wheels and casters, and the base were all donated by Valpo Robotics, so we utilized all of those parts. The base is a 1/2 inch thick HDPE per league standards, and this system housed our entire four-bar mechanism as well as the Arduino and the kicking tee, which would house the ball in the event of a kick. So continuing with the mechanical subsystems, our four-bar mechanism was made out of 6061 T6 aluminum. We chose the aluminum because of its lightweight nature. In addition, we'd also worked with it before, so Stephen knew how to weld the aluminum, so we used that to our advantage, and it was also easy to machine with the tools at our disposal. We used welded joints because in the support frames, welded joints were a lot more sturdy than screws and they required less maintenance. We used bushings and bearings that were donated by Mizumi in order to decrease the level of friction that was occurring within our system as the leg would swing in performing a kick. And we also used a sim motor in order to lift our system out of the dead zone with a 9:1 gear ratio gearbox. Originally we had a 15:1 gear ratio system when we didn't have the surgical tubing attached to it, and with the surgical tubing now on, we were worried that the motor was acting as a brake because it wasn't moving fast enough once the kick was in motion. So we went to a lower gear ratio in order to give us a higher speed in the motor so it would keep up with our system as it actuated through the kick. And for our surgical tubing, we used 3/8 inch diameter surgical tubing with a 1/8 inch wall thickness, which is a little bit more robust than your standard surgical tubing that you find in a doctor's office. So it provided the necessary force required per rung that we wanted in order to actuate our kick, and we managed to get all the way up to 89 feet under full power with the surgical tubing. Continuing in the mechanical section, our tee, as Sadie mentioned earlier, was under iterative testing. We did multiple 3D prints, altering the angle at which the ball was held in the robot by 5 degrees each time. We found that if the angle was too steep, the ball would have a tendency to jump out of the system when the robot began actuating its kick. If the angle was too low, the ball wouldn't travel far enough when the kick was actuated. So in the iterative testing, we tested all the way from 55 degrees up to 80 degrees, and we found that the 75-degree angle that the ball would be held in the robot was the optimal angle at which to conduct our kick. For the foot, we originally were going to test and prototype with 3D printed foots and then switch to a metal foot later. The 3D printed part was made out of standard PLA, but actually we decided to keep that 3D printed part. As Sadie mentioned earlier, we originally hoped that a larger and heavier foot would provide more mass and thus more momentum to our kick, but we found that a faster swing was more important than a heavier swing. And so we ditched the metal foot and instead took our PLA foot and cut grooves in there for bolts so that it would be a lot safer to manage than zip ties, and stuck with the 3D printed foot because of the advantage in speed that it gave us. All right, so for the budget, we were given the same basic $500 budget that senior design teams are given. If you were to design the robot and build it as we designed it, it would cost $1,174.18. But obviously we didn't have that kind of money in the initial budget. But what we did have were savings from Valpo Robotics donated parts and parts that were donated by Mizumi. And those total savings ended up being somewhere in the realm of $803.87. And so the total cost to senior design then to buy our aluminum, our kicking motor, and the surgical tubing was somewhere in the realm of $370.31. So well within our budget. All right, so for future work that we would advocate that Valpo Robotics would do, we would advocate mainly that they upgrade the base and the drivetrain. The base has gone through 2 generations of senior design and 2 seasons under Valpo Robotics. So it's got a lot of holes drilled in it. There are slots that are cut in there, and it could be machined a little bit better than it currently is. So we would upgrade that they get rid of the HDPE base and replace it with something that's a little bit more reinforced and new. We also would advocate that they upgrade the drive motors because the drive motors are also relatively old, and we would recommend that they upgrade them to something that's a little bit more powerful and can drive the robot in a little bit better of a fashion. We also would say that they should replace the casters with some kind of omnidirectional wheel because those would give the robot a lot better maneuverability, and in addition they cost a lot less. And we found that the upgraded cost of these parts would be approximately $200 in just the drivetrain alone, not including the HDPE base. Alright, so what we learned in senior design is, as Stephen mentioned earlier in the semester, robotics is not an exact science. Things will go wrong. We can't account for everything going right in our designs, and we need to be prepared for that. Safety always comes first. This robot is as you've seen, is very dangerous in that 4-bar mechanism swinging, so it's got several mechanical and electrical locks in place in order to ensure that nobody has been hurt, and nobody has been hurt yet. Fingers crossed. So safety always comes first in our designs and in our build work. Be smart about old parts. As the budget slide proved, if we hadn't been resourceful with our donations and our reach out to Valpo Robotics, we would not have gotten those replacement parts, and we would have had to buy those all off of Amazon, Vex Robotics, and various sources, and we would have been way over budget, and we would not have come on a budget like we originally had. And the most important one is planning to be done early isn't early enough. We originally planned to be done with this project early in March and then test throughout the entire month all the way up to competition, so we would be 100% ready to go at competition. That did not happen. After spring break, we were still messing around with the metal foot and doing our testing, and we were working all the way up until April 8th, putting our final touches on and testing through that final week just before the big playoff game on April 8th. So in summary, I would say that what we learned is expect the unexpected. Nothing is going to go to plan. You have to be ready for, let's say, in case your supplier doesn't come through and provide you the parts on time, if something is great in design but it breaks under a lot of weight, things of that nature, and then have a plan in place in case those things happen in order to deal with those results. Alright, so in review of our presentation, we have restated the objective of our project and the building process that we went about in our system throughout the year. We discussed the variations from our design since our last final presentation in December, the testing and the results of that testing, the electrical and the mechanical systems of our robot, the budget of our project, the future work that would be done by Valpo Robotics, and what we have learned as a part of senior design. So, are there any questions?
Having tried both designs, do you think there's potential for just using a motor to drive the foot, or do you need to use some kind of spring or way to store potential energy to get to the system?
So the question is whether or not we think you need to have some sort of potential energy driving a foot of some sort, or if we could just drive from a motor. Through what we've seen, the best results between other robots in previous iterations and other schools, the best results come from some sort of potential energy. We were hoping through the 4-bar mechanism that we could try to avoid a store of potential energy, as you can see it's a lot more dangerous. However, it did end up being the best solution, and I think that is the best solution going forward.
Going off the question, so your surgical tubing, it must have a non-linear spring stitches, right?
So the question's about the surgical tubing and about its spring stiffness. There's not actually a lot of information online about how it performs under tension. Most of it is the skeptical Amazon reviews about people who want to use it as human slingshots. But I would say through what we've seen, it's not linear.
So do you want non-linear or linear spring systems perform better?
I'm not sure if a linear system would perform better. I think in this case, the way it behaves is so out of the norm of how you would normally use a linear spring that it would be hard to determine without testing it.
So one more question with that. You said faster swing is more important than heavier. Wouldn't a heavier foot give you potential energy just of a different point?
So I'll actually answer this with the way that I answer this question is think about how golf drivers have progressed over the years. A lot of golfers, they used to have small, heavy drivers, but now their driver is gigantic and it's all air. This is because they use more speed than they get more momentum from the speed that they hit than from the momentum built up from the heavy mass of the object. That's kind of what we saw in our kicking mechanism. The faster the foot went, the more momentum we transferred into the ball, and the farther it went. Every time we put the heavier foot on, it didn't do anything. It always slowed the system far too much down to be able to get us to get any momentum from any weight.
Recalculations. That'd be interesting.
In your demonstration last week, we saw because it was on uneven floor, the kicker was tipping left and right. I know you mainly play on flat surface, but if you want to do an improvement, so to avoid this, other than adding extra weight, because obviously it's causing more problem than helping, is there what can you do to avoid this issue and not tipping left and right?
So one of the issues we did have was that it does jump a lot when it kicks. And we actually named it Charlie Brown because before we did some adjusting, it did tip over on its back every time it kicked. So really the best way is to fix the weight distribution if you don't want it to kick. Right now, a lot of our weight is on one side of the kicker because the battery and all of everything is mounted on one side. So it would need a little bit of redesign and a little bit of rearranging. And we also have a weight in the front, and it's just in the center, so you could potentially split that weight up onto two sides of it to try to prevent any tipping if you were to play on an uneven surface.
Any other questions? Thank you.